Okay, so let me start with the lecture. But as I can see that not many have joined, so okay, so fine. So maybe we'll start, but in the first few stuff we are going to discuss, maybe we'll be a bit slow, and then if the number of students joined is reaching a certain level, then we can just speed up. Okay. So firstly, the topic of discussion today is the set of irrationals. So, what we know about that? We know there is a set of real numbers. That is a very like most dealt with set among us. So, this is a set of real numbers, and then we have in this set we have a subset of it which is called rational set of rationals, and then its complement. That is all such real numbers which are not rationals, and we call them to be irrationals. Right now, what is the definition of a rational number? So, what is this set? So we know what is the set R. Now let us think about what is the set Q. So what is the set Q? Q is the set containing all such numbers AB such that AB are integers, B not equal to 0 and AB are coprime. Right? So this set is called the set of rational numbers. Now then what is the set of irrational numbers? It's clearly all the numbers, all the real numbers which are not rational. Now we try to deal about this. We try to think stuff about this. So what about the irrational numbers? Okay, first of all, let me just clear one thing. So this is a very common ambiguous thing we do. So what about this number? So what about 4 by 6? So is 4 by 6 a rational number or a irrational number? So this is my definition of rational numbers, and the irrational numbers are all the numbers which are not rational. So what about 4 by 6? And this session is so I forced this session to be live. Otherwise, I could give the recording also. So the only motive of taking live session is the interaction, right? So try to interact as much as possible. So when I'm asking something, so if you have any idea, any hint about it, just reply it in the chat, or you can unmute yourself and speak, so that it is interactive as much as possible. Okay. So for now, the question to all you all is 4 by 6 rational or not? Let me know. What do you think? 4 by 6 is rational or not? So my question is 4 by 6 rational? Okay, so people are saying yes. So let's see what happens. Correct. 2 by 3 is rational. 2 by 3 is rational. So you were saying that 4 by 6 is rational. You were saying this is the case. And 4 by 6 is equal to 2 by 3, which is also rational. So now there is a problem here. So by definition, a set should contain distinct elements, right? But here you were saying 4 by 6 is in rationals, 2 by 3 is in rationals, and again you were saying 4 by 6 is equal to 2 by 3. So in this set rationals, there are two elements which are not distinct. So can this be a case? And again, this is our definition of rational numbers. So how does you think that 4 by 6 satisfies the definition? So 4 by 6 doesn't satisfy the definition, right? Here AB, like 4 by 6, they are not coprime. We need the denominator and the numerator to be coprime by the definition, but it is not coprime. So somehow there is a contradiction if we assume that 4 by 6 is a rational number. So 4 by 6 is not a rational number, to be very clear. Now then the question is 4 by 6 a real number? Is 4 by 6 a real number? So this thing what I'm discussing right now is a very common ambiguous thing. Okay, so just be clear with this. So we came to the conclusion that 4 by 6 can't be rational. Some weird conclusion, obviously. But now let us think that can 4 by 6 be a real number? Okay. So suppose it is. Suppose it is. So if 4 by 6 is real and 4 by 6 is not rational, then 4 by 6 is irrational. But that is completely wrong, right? 4 by 6 can't be irrational. So 4 by 6 is not a real number. 4 by 6 is not a real number. So that is the thing. So all such numbers like 4 by 6, 10 by 15, 100 by 200, they doesn't make sense actually. So we write that 10 by 15 is equal to 2 by, what do you call, 2 by 3. So this 2 by 3 is a rational number, but 10 by 15 is not a number only. So somehow to make ourselves comfortable with it, we have convinced ourselves so far that all such numbers exist and they are equal to their co-prime form or rational form. But individually, the problem is logically they can't be any number. You can think them of as representation of certain number, but they can't be numbers. So they are not real numbers. Okay? This is a weird conclusion to make, but think about it. This is something we never thought about, but this is something like we simultaneously like we spontaneously did mistake on thinking about it. Okay, so that was just a quick discussion, like a silly reminder. But let us not distract ourselves. So let us go to our main topic, which is irrationals now. Okay, fine. So we know these irrationals are the numbers which are not rationals. So let us talk about them. Let us talk about them. Let's see some stuff about them. And again, as I can see, many have joined. So this session should be as much interactive as possible. So when I'm asking something, try to respond. That will be like that will increase the benefit of the class. I think that, and I really believe that. Okay, so let me just erase this stuff. Fine. So now we are into the set of irrationals. Okay, irrationals. Good. Few preliminary questions to ask. Suppose alpha beta are irrationals. Then what can we say about alpha plus beta? Is this forcefully irrational? Is this true or false? Please respond, all of you. I know this is a very easy one, but just please. So it is false. Correct? Yeah. Fine. So it is false.
False.
False. Yeah. So why it is false? So just we can take an example. So to prove something, like to show something is false, we just need to show give a counter example to it, right? Now to prove something true is a difficult part, but whatever. So here we need to show it false. So just take an example like root 2 and minus root 2. So the sum is 0, which is irrational. So now, okay, so from here we are going into our main thing, today's main discussion, that is how to prove something is irrational or something is rational. Okay, so the thing is, okay, so how do we know that root 2 is irrational, first of all? So we will answer to this question, but not now. Not now. Okay. So just remember that this is something we need to answer. Now let us go to the second thing, that if alpha beta are irrational numbers, then what about alpha times beta? So can we imply that alpha times beta will be irrational always? So is this true or false? False. Correct. It's false. Again, why it is false? Let's again take root 2 and root 2 to be alpha and beta. So here we are getting 2. So again we assume that root 2 is irrational. Somehow we'll prove that, or at least like discuss about how to prove that. But then here we are getting that alpha times beta is also can also be rational. Okay. So then we are getting like these all are the stuff, like this is not closed under addition, it is not closed under multiplication. Fine, but one more thing there is, that is a very might be sometimes useful thing. Like if you add a rational with a irrational, then it is always a irrational, right? So this is something we know. But again, just one interesting stuff to discuss. So let alpha beta be rational. Then what can you say about alpha power beta? So can we say alpha power beta is also rational? Someone is saying false. It might be rational. So you're saying like you were telling about this. It will be rational always. So okay. So this is a bit tricky one. It can be rational. So if you think it can be rational, then how you are trying to give a counter example? So if it is, you're trying to show it is true, you need to prove it. If you're trying to say it is false, you need to give a counter example. So how you are gonna make the counter example here work? Try to think about a counter example. E power ln2. Okay, so now you have to show that ln2 is irrational and E is irrational. So okay, so now whenever you are trying to prove something, like give a counter example, just remember each and every term you're assuming to be rational, you need to show that they're irrational. We haven't done yet, right? Correct, correct. So this is a better technique. So we can use certain logarithmic thing, like someone pointed out. Okay, so we can use certain logarithmic thing like e power ln2 or something like that. But for that, we need to show that e is irrational and then that ln thing is also irrational. So better than that, we already have used that root 2 is irrational. So using just root 2 is irrational, let us try to do something. Okay, this is a very tricky technique. So first, let's consider the number a to be root 2 power root. Okay, so can you say anything about the irrationality of a? Like, is a irrational or rational? What do you think? A is irrational or rational? So whatever it is, the point is this is unknown. So till the time I checked, this is a very like a famous conjecture kind of thing. So people haven't yet concluded that A is irrational or rational. So A is something. A is something. A is a real number, obviously. So A is irrational or rational. So if A is rational, then we are done. Then we concluded this. Why? We got A, where A is a alpha power beta form, where alpha beta both are irrational, but alpha power beta is rational. So in this case, we are done. Now, if not, then A is irrational, right? Then take A power root 2. So A power root 2 is something like irrational power irrational form, right? And what is definite, like what is actually this? This is root 2 power root 2 power root. That is root 2 square, and that is 2. That is rational. So if A is irrational, then A power root 2, that is a rational power irrational thing, that is becoming a rational number. So in that case also we are coming up with a counter example. So two cases, if A is rational, then also we are coming up with a counter example, that is A itself, root 2 power root 2. And if it is irrational, then just take a power root 2. There we are getting irrational power irrational, which is coming up to be 2. So thus in any case we are getting a counter example. So this is false. Alpha or beta can be rational. So is the counter example clear, like how we are constructing it? Let me know if it is clear, then we'll move into some new stuff. Only clear to one of you? Okay. I don't think it is very like complicated or something. It is the most basic part of our lecture, so make sure you understand this. Okay, so what we use so far is irrationality of root 2, right? Root 2 is irrational. So how to prove it? So this is a pretty easy one, pretty basic one. In number theory, we had maybe like in expression or other books, we had proved it. So not only root 2, root p for any prime number 2 is irrational. How? Just try the method of contradiction. Assume it is rational, then it is a by b, and then do some number theoretic stuff, square them up, and then take b square over there and do some stuff, and then you will get that, right? So this is something most of you should know. Otherwise, go and search it, and I think you will get that from number theory books and all, maybe in internet also. So it is not a very huge thing to discuss about. So we like in easy manner we know that root 2 is irrational. The proof of it is not very difficult. That is what we know. So now our main theme of the lecture is what else we know. We know stuff like E is irrational. We know stuff like pi is irrational. The first two numbers which comes to our mind if we talk about irrational numbers, and like there are a few other things they are common in transcendental number and so, but for now irrational numbers. So they are weird numbers actually, but again very useful numbers. They are irrational, but we don't have a clue about why they're irrational or what does it actually mean to say they're irrational, right? So this is something which is our aim of this lecture. We are first going to show pi is irrational, and then not like we'll not jump for the proof of irrationality of E. That is something we won't do. But before that, if the time permits, and the thing is, so I will be totally honest here. So I completely like made a presentation for this lecture also, but then I thought I won't use it because I am not quite sure that how much we can proceed in this lecture. So there is obviously a time constraint, but it depends on how you guys interact and develop the intuition of it. So my plan is to first carry out the proof of irrationality of pi in an easy manner. So there are various proofs available in the internet, but most of them uses higher stuff like, so what like they uses higher stuff. Okay, so integral and all. So few use a summation thing. So whatever. So in my thing also, I'm going to use a bit of integral, like a basic notion of calculus, but that is like a very basic notion of calculus. And then after proving the irrationality of pi, we will see a very enriched, a very like what we call it, technical and a very intuitive equivalent form of irrationality. That is a very analytic one. We can get a huge analytic perspective about irrational numbers from that equivalent form. And then if we get time, we'll discuss the proof why that is the equivalent form, and then we can prove irrationality of E using that equivalent form. So all this thing we can do, but that depends on the time. If the time permits, we will do. Otherwise, we will stop where the time instructs us to stop. Okay. So firstly, let's move forward with the irrationality of pi. Proof of irrationality of pi. So the proof I'm going to like state here is a modified Neven's proof. So there was someone like Ivan Neven. So he worked on irrationality and all. So not only pi, but he worked on various like these equivalent forms and all. He had a very solid work on that. So Ivan Neven's proof, and this is modified proof. So firstly, it was modified by someone, I don't know the name, like some mathematician, to make it a simpler version of it. And then it was modified by me, and like a very small modification modified by me, and then it was again modified by someone else. So it is a 4 5 step modification. But the modification we did was either to make it more general or to make it accessible to people with less amount of knowledge. Okay, so let us start the proof. And the proof is in some cases it might be a bit complicated, so my high suggestion is to have a copy, like have a notebook and a pen with you, so that at least the important facts you can write down, because they you need to have to use in the next step or so. Okay, so otherwise I have to go back, like I will erase the board obviously, but I can't go back. So just write down the stuff what I'm labeling as some equation, some useful equation or something. Fine. So firstly, let us do some general construction. Some general construction. Okay. So let n be a natural number and let p and x be a polynomial. P and x be a polynomial, real polynomial. So this is a notation of saying that p and x is a real polynomial of degree n. Okay. Then we define this f and x to be x power n p and x by n factorial. Okay. And capital F and x. So we define small f of x and capital F of x, which depends on n, that given natural number, with using that p of x, pn of x. Now capital F of x, f n of x we define as this f n x minus the second derivative of f n x, and then we have till minus 1 power n f of 2n, like the 2nth derivative of f n. So this is how we define stuff. So the definition should be very clear to all of you, and write down the definition. They will be important in each and every step. So given a natural number, we define p and x, a polynomial of degree n, obviously which depends on the natural number selected. And then by having the polynomial, real polynomial, we can define something like small f n x, which is x power n times p n x by n factorial. And then again we can define capital F n x, which is the alternated sum of the even derivatives of small f. Okay. So in this general setup, we will make a few claims and we will prove that. And then again in our specific setup where we are going to try to prove the irrationality of pi, we will use the claims or the properties we proved here. Okay, so 3 claims we are going to show. So I will erase this. Make sure you have written all this important stuff down. So firstly, claim 1. What is the claim 1? Fn double dash plus Fn is equal to small f. Let me try to give the proof of it. The proof should be very simple. So again, what is f n x? We know it is f n x minus f n double derivative of x, so on till plus minus 1 power n f n 2nth derivative of x, right? Now when you are double differentiating f n, then it will give you here double derivative of small f n x, then minus 4th derivative, right? And plus, and here this will be minus 1 power n fn 2n plus 2 x, right? So summing them up will give you fn x plus fn double derivative of x. Okay, so this will cancel out, this will cancel out, and it will go on like in the previous step also, and it will only give you fn x plus minus 1 power n fn 2n plus 2, that is just 2n plus 2 with derivative of fn x, right? Now just look back to the, so come here and just look back to the function fn. So fn x is x power n times pn x by n factorial. So what is the degree of fn x? I need you guys to answer it. What is the degree of fn x? We know the degree of pn x, just remember that. Any answer? Shouldn't it be obvious? Okay, sorry. So pn x, so I am talking about the degree of fn x. So what do you can say about the degree of fn x? So fn x by definition was x power n times pn x by n factorial. So it is 2n, right? What about others? It should be 2n, right? Is it clear it is 2n? Okay, my voice is clear, right? It is audible. Okay. So please try to respond in the chat, please. So this is my humble request so that the lecture is a bit more interactive. That's the whole point of live lecture. And again, you can ask any doubt anytime. Just feel free to ask. Just stop me and ask your doubt. Okay, so we know the degree of fn x is 2n, right? So then the 2n plus 2th derivative will be 0, right? The degree of fn is 2n, and we are taking the 2n plus 2th derivative of that fn. Now it should be 0, right? Then we are left with only fn x. Thus, we have proved our claim, that is capital Fn plus capital Fn double prime is equal to small f. So is the claim 1 and its proof clear to all of you? So I have to make sure that each and every step is clear, but because all the steps are equally important to reach our final conclusion. So is this clear to all of you? Let me know. The claim 1 and its proof. Okay. Fine. So I will go to the claim 2. So you need the claim 1. Okay, so write it down. So all this stuff, write it down. So claim 2, let's see. So the claim 2 will going to show that, again here we need a very basic stuff of calculus. This is what we are going to show. So this is a very simple one. Just do the calculation. So let's first start with the left hand side. So it is fn dash sine minus fn cos whole dash, right? So if we do that, so firstly we have fn double dash sine, then fn dash cos, then again differentiating this minus, we have fn dash cos minus fn sine, right? This fn dash cos will be cancelled out, and it will give fn double dash plus fn of sine. Now we know from claim 1, fn double dash plus fn will give you small fn, so it is small fn sine. So it's just mere computation, nothing else. So we have proved our claim 2, right? The proof is quite easy. It is just the very basic laws of derivatives, differentiation. Clear to all of you? Let me know. Is the claim 2 and its proof clear to all of you? Fine, fine. And one more thing, just I don't remember exactly, so I'm like confused about it. So what is the exact time the class is going to end? Like this lecture is scheduled to be finished. It started from 11:35, I guess, 35 or 11:40. So it is still 1:15. Okay, okay, fine, fine. We have time. We have pretty much time. So our claim 2 gave us this, and here we are using claim 1, obviously. So till now we did nothing about pi and all. So we did something in a general setup, right? So this is something you shouldn't be confused about. Till now we are just doing stuff on general setup. Some polynomial, some differentiation, some general thing. Now let us see what is our claim 3. The claim 3 is very interesting. It is saying if p and x is an integer polynomial, so this is a notation of integer polynomial. So what does that mean? It means all the coefficients of this p and x are integers. Okay. So we knew that p and x is real polynomial, that is all the coefficients was supposed to be real. Now if it is given that p and x is integer polynomial, then it implies that capital Fn of 0 is integer. So claim 3 is a bit different than the other previous two. In the previous two, we're just proving something, but in claim 3, we're proving something with the additional hypothesis. So here we know if it is also given that Pn is integer polynomial, so not for all polynomials, but if it is also given that Pn is integer polynomial, then we can also say that capital Fn0 is an integer. Okay, so let me prove this. Fine. So let Px be C0 plus C1x till Cn x power n. Then what is Fnx? So this is Pnx, right? So what is Fnx? It is x power n times, so let me write it like this: c0 x power n plus c1 x power n plus 1 till cn x power 2n by n, right? So now just so okay, so we know by definition this capital Fn thing is the sum of the, like, alternated sum of the even derivatives of small f. So we need to calculate the even derivatives of small f in order to find the capital F. So let me just mark this thing. So what is the kth derivative of Fn at the point 0 if k is less than n? So can you say what is this? So just think about it. So in Fnx, the minimum power of x is n. Now if we differentiate this Fn k times where k is less than n, then in each term there will remain some non-negative power of x, right? So just follow my words and make sure it is clear to you. So in each term of Fn, the power of x is at least n. Now when we are differentiating it k times where k is less than n, strictly less than n, no, it shouldn't be that. So just think about it. So when k is strictly less than n, then in each term there will be some non-negative power of x remaining, correct? Now if there is some non-negative power of x remaining in each term and we put x equal to 0, then each term is forced to be 0. So sum of 0, the answer will be 0. Is this convinced? Are you all convinced about this? Let me know. I think someone does have his or her mic unmuted. A lot of sound which is coming, so try to mute yourself. And if you have any doubt, please write it down. Yeah, I am repeating. Okay, fine. So you can just see each and every term in this f and x is having power of x more than n, right? Now, when we are differentiating it k times, when k is less than n, then in each term, like when you are differentiating this term k times, where k is less than n, there should be some positive power of x remaining after the differentiation is done, right? Again, in this term, if you differentiate it k many times and k is less than n, so this is n plus 1, then there will be some positive power of x remaining, and so on till all the numbers, like all the terms here. So in each term, there will be some non-negative power of x remaining. Some x power, here it will be x power n minus k, here it will be x power n minus k plus 1 something. Now when we put this x to be 0, then every term will be 0 individually. So the sum will be 0. Correct? Yeah. So if k is less than n, then the kth derivative of fn is equal to 0. It should be clear. Okay? Okay. So for k less than n, we know that this derivative is something we know about. This is equal to 0. Now let us think about it. So let us think about for k greater than n. So I will write down here for k greater than n. So if k is greater than n, there is some place where the k is. So let me write down, it is here. So about ck x power. So what it should be? So not ck actually. So it should be n k minus n, right? So the power of x is k, and the c is k minus n. Because just this is something to observe. The sum of the index of the coefficient and the power of x is always n. So 0 plus n is equal to n. Sorry, not the sum, the difference. So n minus 0 is equal to n, and 2n minus n is equal to n. So here the power of x is k. So now I assume that k is greater than n and less than equal to 2n. So there should be some power of x which is k, right? And then the corresponding coefficient will be c of k minus n. Fine. So we are differentiating it k many times now. So if we differentiate it k many times, just think about it. So all the terms here will be vanished, right? So now I am trying to find out this. So all the terms here will be vanished. Why it will be vanished? Yeah, now you are correct. So why it will be vanished? Because all the terms have power less than k. So if you differentiate something k many times having power less than k, obviously it will vanish. And again, for the terms above it, this is the same logic as the previous one. For all the terms above this x power k, there will be some non-negative, not like some positive power of x remaining there. And now when you are trying to calculate the value at x equal to 0, then this x equal to 0 will make all such terms here 0, because all have some power of x. So only term remaining will be this, right? Now when we differentiate it k many times, it will give you k factorial, right, times c of k minus n by n factorial. This is what it will give. Clear to all of you? Let me know. So this step clear to all of you? Fine. So okay, so please again don't call me sir. So I am just maybe 1 or 2 or 3 years, some finite number of years senior than you. So just please don't call me sir. You can call me Dada, you can call me by my name or something. Okay. So this thing is obviously an integer, right? Because k is greater than n, so k factorial by n factorial is an integer. n factorial, like n factorial divides k factorial, and ck minus n is an integer because pnx was a integer polynomial, was an integer polynomial. So this thing is an integer, right? And again 0 is obviously an integer. So when we sum this up, so all the derivatives of fn at the point 0 will be integers. Now if that is the case, then let us just try to think about this. So that is the case, then what about fn of 0? Fn of 0 is nothing but fn 0 minus fn double prime 0 something, right? Now each of the terms we have proved, we have showed that all the terms are integers. So thus the sum or minus something, this all this linear combination will be an integer. Thus we prove that if capital Fn of 0 is an integer, if that Pnx is an integer polynomial. So is the claim 3 and its proof clear? Let me know. Clear to all of you? Okay, fine. Fine, so I'm going to erase it, but just remember all the three claims are very important to prove our irrationality of pi. We are almost done with the basic or general construction. Now we are going to prove the irrationality of pi. Okay. So I will give you a very short break of maybe 2-3 minutes. Go through the above three claims and understand the hypothesis we had. Like all the stuff we had, Pnx, Fnx, capital Fnx, go through the definition, go through the three claims we proved. Okay. And when you are done with this, I will give you 3 minutes of time and then we can move into the specific proof of irrationality of pi. Okay. So there is something important going on, I think, and I am missing it because of this. Okay, fine. So yeah. So just let me know, is it is good news or bad news? For sure. You know what I prefer, so okay, fine, fine, fine. So let me go to the actual proof of irrationality of pi. Fine. So let assume the contradiction. So now we are going to show that pi is irrational. So assume the contradiction that pi is rational. If pi is rational, then pi is equal to some a by b. Correct. So now for all n natural number, define a polynomial. So given a n maybe, so you can just think as for l or given a n arbitrary n natural number. Define p and x to be a minus b x whole power n. So just note p and x is a polynomial satisfying exactly the construction of our general construction. Okay, p and x is a polynomial, real polynomial of degree n. Then similarly construct small f n x and capital F n x as we did in our general construction. So we know how to construct small f n x. So let me just remind it. It is x power n times p n x by n factorial. And then again we know how to construct capital F n x. So similar to the general construction. Okay. So in this specific case, we are just dealing the specific polynomial a minus bx power n. Okay. That is what we are doing. Fine. So the results we have shown, like, okay, so we know that, so what we know from our claim 2, so let me erase this. So in the previous general construction from the claim 2, we know this, right? What do we know? We know if, and I just told you to write it down, so just make sure you were checking that previous thing. fn cos whole derivative fn sine. We prove this. So this will hold exactly the same way here, because that was done in general setup and now we are doing a specific setup. So this should hold here. So it can, we can say here that integral of fn sine is equal to capital, the indefinite integral capital Fn dash sine minus capital Fn cos. Okay. So here we can say integral from 0 to pi will give you this. Okay. From 0 to pi. So what is this from 0 to pi? So Fn dash pi sine pi minus Fn pi cos pi whole minus Fn dash 0 sine 0 minus Fn 0 cos 0. So it will be okay. So the sine pi will be 0 minus cos pi will be there. So just do it and it will give you Fn 0 plus Fn pi. So is this what it is giving, right? This is minus 1, cos pi is minus 1, and again sine of 0 is 0 and cos 0 is 1. So minus minus cancel out. So Fn 0 plus Fn pi. This is what you will get as this. And we are doing this from our claim 2. So is this clear to all of you? Let me know. So we concluded that 0 to pi integral of small fn sine will give you capital Fn 0 plus capital Fn pi. Clear to all of you? We are using our claim 2. Okay, fine. Let me write down the conclusion here. By using claim 2, so let me also write down what we assume here. We assume pi is a by b, and we assume p and x is a minus bx whole power n. And now we got the integral 0 to pi fn sin x, like fn sine is equal to capital Fn 0 plus capital Fn pi. Okay. So one more thing I need to be clear about is, so what is the definition of pi? Okay, so to prove some number is irrational, we need to know what is that number. We can't use the very basic definition of pi by saying pi is something like ratio of the circumference and the diameter. So this is something we can't use like that. We need to show that firstly the ratio is constant and all. So we need to show, like, we need to use some definition of pi which is very handy to use. So I will use this definition of pi. So I will define pi as pi is the smallest number. Pi is the smallest number where sine of x is smallest positive number where sine of x is 0. Correct. So we need a bit more algebraic definition which we can use here. So firstly, so maybe I should have mentioned it before only. So knowing the definition we are going to use, then we motivate ourselves to have a proof or have a construction like this. So what is pi? Pi is the first number, positive number where sine is 0. And moreover, you can use that sine of x is in 0 to 1 closed interval in, like, when x is in the interval 0 to 5. Okay. And again, we know that cos of pi is minus 1. So you can use all such stuff, all such properties of pi. So I am going to show what is pi to us. So pi to us is a real number, the first positive real number where sine is 0, the real number for which when x is in that interval from 0 to that real number, sine x is in 0 to 1. Pi is a real number where cos is minus 1, the value of cos is minus 1. So now we are going to show any real number satisfying the three properties can't be rational. It is bounded, like it is always irrational if there is some real number satisfying these three properties. Now we know pi satisfies these three properties, so pi is irrational. That is our argument. That is our formulation of argument. Okay. So just let me finish this up. Fine. So now just think this. We know in this integral, okay. So in this integral, x is from 0 to pi, right? That means sine x is from 0 to 1, correct? Now again, just note p and x, by definition of p and x, it is always greater than a power n, correct? If x is greater than 0, it is always greater than a power n, sorry, less than a power n. And just note it is greater than 0. Why it is greater than 0? Because x is less than, so what is pi? So you know pi is a by b. And here if x is less than a by b, then a minus bx is always greater than 0. So it is always positive, right? P and x. Thus we can say, now what about f and x? F and x is x power n times p and x by n factorial. So f and x should be less than, x is less than pi. So f and x is less than pi power n, x power n, pi power n. Then p and x is less than a power n by n factorial. And then it is always greater than 0. All the terms here is greater than 0. Then f n times sine. So sine is greater than 0, less than 1. So the inequality will remain same. So pi a whole power n by n factorial, and this is greater than 0. So is the whole discussion clear to all of you here? Like we concluded that f and sine, this thing should be, when x is in 0 to pi, should be greater than 0 and less than pi a whole power n by n factorial. So is it clear to all of you? Let me know. Okay. So write down the conclusion again. Here we concluded this. Okay. So from here, so this function is greater than 0 and less than this term in the interval. So by a basic property of integration, we can say 0 to pi integration of this function f and sine will be less than the length of interval, that is pi, times the maximum value attained by it, or the maximum value it can attain, that is pi a whole power n by n factorial, and is greater than obviously 0. This is something we can say, and very important. This we'll use here and there. Okay. So just notice this. We use this thing here. So here you are using the definition of pi, right? And again, before that, we use that cos of pi is minus 1. So there also we use the definition of pi, that is property of pi. So this is something we are going to use. So let me erase all of this. Then I will state you a very basic, like what you can say, basic property of limit of a sequence. This is something, if you are comfortable with limit of sequences, you will know. But if not, then just assume this is true for now. So this sequence, so let me just write down in a specific case only. This sequence, so if you consider this as sequence on natural number n, so this goes to 0 as n goes to infinity. What it is saying, you can make this term arbitrarily small, taking arbitrarily large n. So this is a case, this is something we know from analysis, that is c power n by n factorial goes to 0. Okay. C for any constant. You can try to show this, but not here. Let me just assume this. So it goes to 0 as n goes to infinity. If that is the case, then pi times it will also go to 0. It is just a constant multiple as n goes to infinity. So from here we can say there exists a capital N in natural number, arbitrarily large n, such that this term pi times pi a whole power n by n factorial is less than 1 and greater than 0. Greater than 0 is obvious, but at least less than 1. Because this term, okay, so here it should be capital N. Sorry. Because this term is going to 0, we can make it smaller than capital N, obviously. Sorry, smaller than 1, obviously. So is it clear this part, that why we should get a capital N in natural numbers, such that this capital N thing, like pi times pi a whole power capital N by capital N factorial, is less than 1? Is it clear to all of you? Let me know. Then I will move to the next step. If you have any doubt, just ask me, okay? Okay, fine. If it is clear, it's fine. So now from here, what we can say is, there exists a capital N in natural numbers such that, so here that n, small n can be, we can represent capital Fn, and capital Fn sine 0 to pi integral is less than 1 greater than 0. Right? So this is our biggest confusion. We'll use this confusion and make sure you have written down this. Okay, we got a capital N such that f capital Fn, like f capital N sine integral from 0 to pi is less than 1 and greater than 0. Okay. So write down this, and I will erase the blackboard, and then we will just move to our next step. Okay, you can take 2 minutes to figure all this thing and just make it clear to you. Okay, fine. So let me erase this. So from the previous thing we had, that is 0 to pi. So maybe I would say this in the previous canvas only, but here, so for capital N, so capital N is optional like this. This is less than 1. Now we remember that this is equal to this, right? This we showed from our claim 2, which proved this. Right? Is it clear? So for capital N, we got this. So again, write it down. This is also very important. Fine. Now I will, like, we will see a very small observation. That is, just check f and x. That is by definition x power n a minus bx whole power n by n factorial. Now what is fn of pi minus x? That is pi minus x whole power n times a minus b. Again, okay, so let me write it down here because there is no space out there. So firstly, what is pi? Pi is a by b. So I will write a by b formula. So a by b minus x power n. So we are replacing x by this, and then a minus b times a by b minus x whole power n by n factorial. So this will give you a minus bx whole power n by n factorial times b power n, and here a minus this, a minus a will cancel out, a minus a plus bx whole power n. So this will be, a minus a will be cancelled out. This will give b power n times x power n. So b power n, b power n cancel out. So this will give you x power n a minus bx whole power n by n factorial. Is exactly same as fn of x. So we can just see fn of pi minus x is exactly same as fn of x. Okay. So this function is actually symmetric, like symmetric about this. So if there is x here, okay, and if there is pi here, then pi minus x. So where should be pi minus x? So something like here. So okay, so let this be 0. Pi minus x. So whatever this is the case, so if that is the case, okay, so fine. So it is symmetric about pi by 2, right? Something. Okay. So this is the case. this function is always symmetric about pi by 2. So the value at pi minus x will be exactly same as the value at x. Now if that is the case, then all the derivative will also do the same, kth derivative, right? The kth derivative will also do the same. So just let's consider specific case. Just make it, so let me erase this whole part. So we know this function f of pi minus x. So let us consider capital N. We don't need to consider any arbitrary n, only capital N considering will be enough. Capital N. So capital N is a specific number for which we did that thing. We took that capital N to arbitrarily large so that that integral is less than 1. So for that capital N we are working with. The capital N of phi minus x is equal to capital N of x. So if that is the case, we know that the k derivative will also be same, and we just consider it as a specific point, that is pi, like put x equal to 0. At least this should be the same. Now again, okay. So now our interesting part. So we knew that these all are integers. From where we know this? Our claim 3. Okay. So just remember that Pnx is here an integer polynomial. Pnx is an integer polynomial. Correct? So just go back to our claim 3. If Pnx is an integer polynomial, then all these kth derivatives are integers. So if these are integers. And from there we concluded that capital Fn of 0 is an integer. So similarly here capital Fn of pi will also be an integer. So all of this is coming from our claim 3 of our general thing. Clear now? Let me know that this is clear or not. So here the stuff about 0 will exactly be the mirror image of the stuff about pi. Now as we know that capital Fn of 0 is integer, then we can also say capital Fn of pi is an integer. Is it clear? Is it clear to all of you? Let me know. Okay, why do I have the absolute value sign? Okay, that is a good question. When you are taking derivatives, okay, when you are taking derivatives, there might be absolute value sign, right? Shouldn't there be? I think there should be. Or yeah, they might be same only. Okay, at least that is not causing a problem. So because I took the derivative thing, so I just okay, there shouldn't be absolute value like this. But whatever. So this is not wrong at least, right? Yes, is it clear to all of you, right? So we got that capital Fn of 0 is an integer, and with that capital Fn of 0 is an integer, we can conclude from directly from claim 3. Because we know Pnx is an integer polynomial. But here, as we know that 0 and pi are doing almost the same thing, we can conclude that capital Fn of pi is also an integer. Correct? So now what we can say is capital Fn of 0 plus capital Fn of pi is an integer. Right? Yeah, capital Fn of pi is equal to capital Fn of 0. That is correct. That is correct. So now we don't need that actually, so I didn't mention that, but whatever we need is this. So we know this is an integer. Again we know that capital Fn of 0 plus capital Fn of pi, this thing is less than 1 and greater than 0, right? But how can these two simultaneously hold? An integer can't be lying between 0 and 1, right? So that is our contradiction. Sorry for this horrible handwriting, but okay. If it is clear, then it is okay. The point is, any integer, no integer can be lying within 0 and 1. Okay. Thus, this is a contradiction. And thus, we can say our initial assumption, because pi is rational, was wrong. So we are done. Okay. So it's time to just recall the whole proof. Just go back to the proof. No hurry. I will give you 5 minutes time. And after you look around the whole stuff what we're doing, just let me know in the chat, was the proof clear to you up to some extent, and then you can just go through it after the class and it will be more clear to you. But for now, was the proof clear to you? Let me know. Okay. So no, I am not showing that this is the case. Okay, I am not showing what you are saying is the case. That capital Fn of x is equal to capital Fn of pi minus x. That will be the case maybe, but I am not showing that. I am just showing the small f part. So just do the trivial computation. You will get the small f of nx is equal to the small f of n pi minus x. This is just by algebraic computation. And then I am saying if that is the case, then derivatives will be the same. At least the mod value will be the same. Why I am saying about the mod value? Because there is x here and minus x here. So in each of the derivative, there will be a minus 1 here and minus 1 there, right? That's what I'm saying. Okay, so is the proof clear to all of you? The whole proof, let me know. Fine, fine. Okay. So now we are moving forward to see. So maybe I won't be able to give the proof of both the direction, but okay. So let us try to discuss it. So nothing to worry about. Whatever we are learning here is something like we should get a new perspective to it at least. If we not get the proof, proof is not something which does matter very much. You can just go to, like, it is nothing very uh, exclusive here. You can go through the proof afterwards also. So just let me just wait a second. Fine. So first of all, what can you say about the density of rational? So let me just claim it like this. So if you guys know sequence, then this is something very pretty much clear. So if root 2 is there, if root 2 is there, then suppose this is root 2. Root 2 is an irrational. Then if we take a neighborhood around root 2, a very small neighborhood around root 2, then can we have a neighborhood around root 2 which is containing all nothing but rational numbers? Like there is no irrational numbers inside that small neighborhood. Can we make it like that? No. Correct? So there will always be some irrational number very much close to it. Sorry, some rational number very much close to it. So what we can say is, for so this is not only for root 2, for all numbers. So let's say for all x naught in R, there exists Qn, let's say Qn, where Qn is a sequence of rationals such that Qn converges to x naught as n tends to infinity. So for any real number, you can get a rational convergent sequence to it. That is a sequence of rationals converging to it. Okay. So for irrational also you can get that. So for any rational number, you will get a sequence of rationals converging to it, right? So I will define something as a two-well rational approximation. This we call as a rational approximation of a real number. Okay. So then, okay. So suppose alpha be a real number. So now I am defining something. So alpha be a real number, and suppose Pn by Qn is a sequence of rationals converging to alpha as infinity. So what we know is alpha minus Pn by Qn goes to 0 as n tends to infinity. That is Qn alpha minus Pn by Qn goes to 0 as n tends to. Now there is a possible case where Qn alpha minus Pn also goes to 0. So what we need is Qn alpha minus Pn by Qn goes to 0. But there can be a case where this is the Qn alpha minus Pn, this absolute thing goes to 0, not the ratio. So if this is the case, we can tell this, but if this is the case, we can't always tell this, right? This is a very specific case. So if this is the case, if this holds, then we call that Pn by Qn, this rational sequence, is a two-well rational approximation. Two-well rational approximation, RA. Okay? So this is a rational approximation to alpha if this is the case. If the sequence converges to it, it is a rational approximation. But I am saying if the sequence converges to it, and not only that, only this Qn alpha minus Pn thing goes to 0, then we say this to be the two-well rational approximation. So all, just note this, that all rational approximations may not be two-well rational approximation, but any two-well rational approximation is an approximation, rational approximation. Some gray rectangle blocking the backboard. Okay. So I can't see it, whatever. So let me just, okay, so I will write it down here. So if this is 0, then I am saying this to be, this Pn by Qn to be 2L rational approximation. Okay, this is what I am saying. Now there is a point to think about. So let me use about. So let me just sum up a bit. So Pn by, let Pn by Qn. Okay, I will repeat. I will repeat. Yeah. So if Pn by Qn is a sequence of rationals such that alpha minus Pn by Qn goes to 0 as n tends to infinity, then we say what? Pn by Qn is a very obviously what we say it to be a rational approximation of alpha. Correct? Now if Pn by Qn is a sequence of rationals such that Qn alpha minus Pn goes to 0 as n tends to infinity, then we call this to be a 2L, what we call, like which we call Pn by Qn, this rational approximation to be a 2L rational approximation of alpha. So just note that this is obviously this, if there is some 2L rational approximation of alpha, then that 2L rational approximation is also a rational approximation of alpha. So because if this is the case, then this is also the case, but not the converse is true. Like if this is the case, this may not be a case, right? So are you guys getting what I am saying? Is the definition clear? 2L rational approximation or not? Fine. So for those who had doubt in it, is it clear? Okay. So now I will state a very strong result. So this I call it to be the approximation theorem. I don't know if there is a name to it proper. So what I'm claiming is if alpha be a real number, so alpha, if alpha is a real number, then alpha is irrational if and only if there exists Pn by Qn, a sequence of rationals obviously. So here we have to mention Qn is not equal to 0 and all that. Okay. Pn, Qn integers and 2 prime and all that. There is a sequence Pn by Qn which is a, so let me just write it in the normal form only, for which Qn alpha minus Pn goes to 0 as n tends to infinity, but Qn alpha minus Pn is never equal to 0. Okay. So what I am claiming is if Pn by Qn is a sequence of rationals such that it is a 2L rational approximation of alpha, it is a 2L rational approximation of alpha, but none of the term Qn alpha minus Pn is equal to 0. But actually they are going to 0 as n tends to infinity. So if this is the case, then alpha is irrational and vice versa. Like if alpha is irrational, then we will find a 2L rational approximation of it such that none of the term Qn alpha minus Pn is 0. So this is the statement of the theorem. So maybe we will prove the easier direction now. I don't think we will have time to prove the other direction. And by this theorem, you can try to show the irrationality of P. Okay. And there are very other good stuff about this also, but maybe we won't have time to discuss about them. So again, so what was the time? 1:15, right? Okay, so yeah, we have time now. So is the at least statement of the theorem clear to all of you? Let me know. Or if there is anything you need to discuss about, tell me. Okay. Fine. So maybe we will just okay. So which part do you think is easier? So I think this part is easier. So should you give it a try, or I will tell the solution? This is a, like Olympiad problem kind of thing. This thing very easy. So easier than Olympiad problem too. So, will you try to prove this reaction, or should I discuss the proof? Okay, as there is no answer, so I will discuss the solution. Okay, let me erase this. So what I will show now is what I will show now is assume that okay. So assume alpha be a rational. So assume the contradiction. So alpha is rational, and there exists a Pn by Qn sequence, which is a two-well rational approximation of alpha. That is Pn by Pn minus Qn alpha is going to 0 as n tends to infinity, but Pn minus Qn alpha is never equal to 0. Correct? Okay. So now just okay. So alpha is rational. If alpha is rational, alpha equal to some a by b. So Qn alpha minus Pn is equal to some Qn times a by b minus Pn. Correct? And that is equal to b, and here it should be a Qn minus b Pn. Right? Fine. Now this is never equal to 0. So this is never equal to 0. Now aqn minus bpn is always an integer, correct? Because a, b, qn, pn all are integers. So now never equal to 0. Thus mod of this thing is greater than 1, greater than equal to 1. Integer greater than equal to 1 because it is not 0. So this thing will be greater than equal to 1 by mod of b. Right? Now, if it is greater than equal to 1 by mod of b for all n, then how can it converge to 0 at n goes to infinity? So it was supposed to converge to 0 as n goes to infinity. But this can't happen, right? Because it is greater than equal to 1 by b. That is a contradiction. So we assume that alpha is rational, so it is a contradiction, so alpha is irrational actually. So we prove this part. So if there exists a two-well rational approximation of alpha such that the thing Pn minus Qn times alpha is never equal to 0, then alpha can't be rational. That is, alpha is always irrational. So is it clear? Is it clear to all of you? Let me know quickly. So which part? So okay, so Qn alpha minus Pn is equal to this thing, right? So I just replace alpha by a by b, so it is equal to a Qn minus bpn by b. Now a Qn minus bpn is never equal to 0 because this term is never equal to 0. So this term can't be equal to 0. Now again it is integer, right? So mod of this thing will be greater than equal to 1. Any integer, non-zero integer, for that mod of that thing will be greater than equal to 1. So this whole thing will be greater than equal to 1 by mod of b. So now there can't be a sequence which is always greater than equal to 1 by mod of b but converging to 0, right? That's the contradiction. Okay, so maybe we will do one thing. So okay, so just tell me something. If we try to prove some number is irrational using this thing, what we will do? We'll try to construct a sequence of rationals for which that sequence is a two-well rational approximation to the number irrational number. And then again, what we need to have is that Pn minus Qn alpha is never equal to 0. If we get such a sequence, we can conclude that that number alpha is irrational. And for that, we don't need the other direction, right? If we want to prove some number is irrational, this direction is enough. that if there exists a two-wheel rational approximation of it such that none of the terms is 0, then we can say that number is irrational. So to prove irrationality of some number using this theorem, we don't need to have the other direction. So let us forget about the other direction and just see a quick application of it, and by that we can end the class. And I just mentioned that the other direction is also true, and that is a much more analytical question to answer, that for all relationals you can get some sequence like this. So that will give you a satisfaction that if you try to find a such sequence, then you won't be fail to find such sequence for any irrational. Okay. So whatever. So let us have a quick application of it. So let us try to prove irrationality of E using it. Okay. So by definition, E is this, right? Right. So now let us define Qn to be n factorial and Pn to be n factorial plus n factorial by 1 factorial till n factorial by n factorial. Now Pn by Qn, what is that? Pn by Qn will be 1 plus 1 by 1 factorial till 1 by n factorial. Correct? So if Pn by Qn is this, then we can say E is equal to Pn by Qn. So I define Pn by Qn like this. So what we need to do, we need to find a two-wheel rational approximation to E such that a two-wheel rational approximation to E, we can name it as Pn by Qn, such that Qn E minus Pn is never equal to 0, but is going to 0 as n tends to infinity. So now this is, you can write E as this plus k equal to n plus 1 to infinity 1 by k factorial, because this is the sum from 1 to 1 by n factorial, right? Now if this is the case, let me erase this part. So is this definition of Qn and Pn clear to all of you? Let me know quickly. What we are doing so far is clear to all of you, then I will erase this. Okay, fine. So maybe our lecture was a bit too fast for you to digest in one day. So okay, fine. So you guys are good students actually. Like uh, you qualified for a camp. You guys know advanced stuff from like 10 plus 2 or maybe before that also. So I expected that this will be fine for you, and I'm very happy to see it is fine for you. Okay. So it's a very good progress actually. So if this is the case, then let me just do the thing. So okay, so Qn, so by just algebraic computation, Qn times E minus Pn, Qn times E minus Pn is equal to Qn times k equal to n plus 1 to infinity 1 by k factorial, right? So now what is Qn? Qn is n factorial. So it is summation of, so what is it? N factorial and summation of, okay, so let me just write it down in a easier looking form, n plus 1 factorial, n plus 2 factorial, so on, right? So we got this. So if this is the case, then just observe that this is equal to n factorial by n plus 1 factorial plus n factorial by n plus 2 factorial and so on. Now this is less than 1 by n plus 1. So this is actually equal to 1 by n plus 1, whatever. And now this is, so what is this? This is 1 by n plus 1 times n plus 2. So this is actually less than 1 by n plus 1 whole square. Now again the third term here is equal to 1 by n plus 1 times 1 by n plus 2 times 1 by, like 1 by n plus 1 times n plus 2 times n plus 3. Now which is less than 1 by n plus 1 whole cube, right? And we can go so on. So this can be less than a geometric series, infinite geometric series of like this. So what is the value of this? This should be, okay, so a by 1 minus r. So what is a? 1 by n plus 1 and 1 minus r. So what is r? 1 minus 1 by n plus 1. So it will give you what? 1 by n, right? So this thing will cancel out and give you 1 by n. So is this whole thing clear, that how this whole computation went? Let me know quickly, then I will go to the next part. So we showed that qn e minus pn is equal to qn times this thing, and then again qn is n factorial, so I just did computation. So let me know, is it clear to all of you quickly? Only one replied, I guess. What about others? Is it clear? Please let me know so that I can continue. If it is not clear, then again, okay. So about the inequality, so let me erase this hanging parts. So I will have n factorial by n plus 2 factorial. So what is that? That is 1 by n plus 1 times n plus 2, right? Let me write it down like that. This will be 1 by n plus 1 times n plus 2. And the next term will be n plus 1 times n plus 2 times n plus 3, right? And so on. Now the second term is less than 1 by n plus 1 whole square, because n plus 1 is less than n plus 2. And then again this thing is less than n plus 1 whole cube. So on you can go. And this will form a, like this is strictly less than a geometric series, which is like this, which can give you this thing to be 1 by n, right? So what is our conclusion from all this? Is we can, this thing is qn e minus pn is less than 1 by n, and obviously qn e minus pn is greater than 0, because this thing is equal to what? This thing is equal to n factorial times summation k equal to n plus 1 to infinity. Okay, so 1 by k factorial. So this is obviously greater than 0. This is obviously greater than 0. Greater than 0. So it is never equal to 0, but so this is by Sandwich theorem we know, limit n extends to infinity, a n e minus pn is equal to 0. Thus this sequence is going to 0 as n tends to infinity, but none of the terms are actually equal to 0. Okay, thus we can say that E is irrational. Why? Because there exists, so this is a two-well rational approximation of P, such that none of the individual terms are 0, and thus we can say E is irrational. So we actually prove irrationality of P. So just go through it and tell me, is the whole part in the whole lecture what we did, the motivation of it was clear to all of you? I need just one more this sanction from you guys that it was okay. Then we can leave. Okay. So the stuff was like this. So this irrational thing is actually underrated topic. Like no one does work on this much, but there are lots and lots to think about this. Yeah, fine. I can give you 1 minute. Yeah. So today, what I could tell, I discussed today, but there is a lot more actually into it. Lot more into it. Okay. So maybe okay, we won't get much time after this, maybe. But yeah, I think you all guys have my phone number from that limit thing only. So if you want to work on this, if you want to study on this, you can just so there is a book Ivan Evans on irrationality and proofs. So you can just read that also. So this is a topic which a mixture of uh, what you can say is this is mostly a branch of analysis. So analytic reformation and also a few part of number theory. So these are like a mixture of analysis and number theory, but not exactly this analytic number theory. So it is different from everything, a very separate and interesting topic. And I am personally working on this summer. I have been working on this under some professor actually. So yeah, if you have anything to discuss about after this also. This was just a quick introduction to our work, like what we did and all. Okay. So if there is no doubt, so Anubhav, is this okay to you? Okay, fine. So I hope that this lecture was interesting and understandable at least, if not interesting. So fine, and just stay safe, stay good, do good mathematics. Okay. So let me stop the share, and before that, let me stop the recording.